Thank you, Professor Yin. It's always a pleasure to be here. 5 years ago, when I started this program, I was here to present the vision for the transportation program. And now it is 5 years later, we have a flow, right? As Professor Yin mentioned, that in the last 2 years, I took a leave of absence. I worked in Didi in Beijing for 2 years. And so today, what I'm going to present is sort of half of transportation researcher, half of transportation practitioner. So you will see some of these topics are very, very different with what you usually see in your classes. But that's how today's transportation evolved. And you will also see that some of the topics are quite different, but it's very, very much related with what's the current, with the current transportation system changes. Before I start, I do want to spend a couple of minutes just to introduce a little bit more in terms of Didi, which I worked for 2 years starting from 2017. And Didi is, like has been mentioned, like Professor Yin has been mentioned, is a Uber's counterpart in China. It's probably the largest in terms of number of trips being served every day. And so every day, the number of trips being served, 30 million. I think it's probably more than that right now. This picture I got, it's from a year ago. Now even on Didi's bike services in China, what I just heard last week was Mid-Autumn Festival in China, and on that day, that just the bike services saw exceed 10 million trips per day, and it's become the second largest in terms of number of bike trips in China. But overall, in terms of also the number of trips, is comparable to the total trips being served by taxi in China. So the whole taxi add up all together is comparable to the number of trips being served by Didi. And so on Didi's platform, there's a series of products being offered to consumers that include taxi, include express, premier, designated driving, car sharing, luxury car service also. And beyond to the individual consumers, Didi also work with cities, and that including public transportation system, clear energy solutions, and also smart transportation, which this is the business unit I led in the last 2 years. I established this business unit and I led that unit for 2 years. Didi now also become a global company. This obviously started in China, but offers service now in I don't know how many countries, but many of the South America countries has Didi. The largest one outside of China is Brazil, Chile, Mexico, and then recently Australia, Japan, some of the European countries as well. So there's a large number of trips being served every day on Didi's platform. Didi also have a lab in the US and in San Francisco, and in Mountain View, San Francisco. All of the overseas services in terms of the particular South America services all being served in the US, start in terms of the cloud services. So anyway, so that's sort of the introduction, very brief introduction in terms of Didi. The reason I want to mention that is to give you just a background in terms of what this company is, and then when I talk about transportation engineering, transportation research, a lot of these the topics I'm discussing with you it's drawing from the experience I was with Didi. I also want to mention this platform service economy. Didi is a platform, is a transportation platform. Sometimes we call it one-stop transportation platform because on that platform you have a number of products. And the platform economy or platform service economy is really started in the US. And as you can see, some of the largest companies in the world now are all platform companies. And if you look into the top 10 companies, 7 of these are platform companies. And in the world, from the world perspective, you can see platform, the global platform, mostly reside either in the US or in China. So, and US obviously has much larger in terms of platform economy. And you can see this picture is really early. This is end of 2017. At the time, you can see that's Uber over there. And Uber's valuation is much larger than that right now. And this is the again, the reason I want to mention the platform economy is that the work we're doing in transportation, a lot of these are related, associated with platform. And even some of the works I'm doing with Didi, and we're trying to create platforms as well. And the transportation engineering services is also changing into, some of these changing into platform type of services.
So Didi was valued higher than Uber?
At one time, it was 58, and Uber was 48 at that time, 48 billion at that time. That was the lowest for Uber in 2017. And with that valuation, SoftBank invested about 8 billion into it, and so the
so now it's
valuation
something somewhere near 60.
I'm not sure the current on the current market. I think it's somewhere around 60. And the IPO value was 72. So it's actually below IPO now. And Didi is still a startup company. It's not IPO yet. I don't know when they will IPO, but still it's a startup company. But it's a very large startup company. It has 13,000 people globally. Okay, now getting into the topic I want to discuss. So I want to start with the transportation evolution in the last about 100 years or so. And this is what I think is the first revolution in the last 100 years. And this is in 1910, around at that time at the city of New York and the Fifth Avenue. At that time, you can see most of these are horse-driven cars, carriage, and there's very little, very few cars at that moment. If you look into the same street 13 years later, and this is what happens. And so people, the transportation tools we utilize changed from horse-driven carriage to cars. Okay, and you can see also there's saying where's the car, then there's where's the horse, where's the horse. There's only one horse on the street at that moment, 13 years later. And really, this is being amplified by Ford Model T mass production of cars, and that changed people's mind in terms of distance and time. You now can travel longer distance with much shorter time, so that you can live further away from the city. And the second revolution, I think, in the last 100 years in terms of transportation, surface transportation, I think it's the construction of the US interstate highway system in 1950s. And with the interstate network, people can travel much further, much faster. So over a few hundred miles, you all drive. And that also changed in terms of people's perception of time and distance. What we are experiencing right now, after 2010, around 2010, I think it's the third transportation revolution. And the three key words in terms of this time in the transportation revolution is connected and automated and shared. In this seminar, I'm going to discuss on each of those. Okay? And so, if you look into the current transportation system, if you take the introduction class, we always say the transportation systems, the surface transportation system, has three major components: the users, the travelers, the vehicle itself, and the infrastructure. Okay? And what traditionally in a transportation engineering program, we focus more or less on the infrastructure and also the users. So we study transportation demand, study travel behavior, and study in terms of how people behave, how people use transportation tools. For us to do a better planning and management of the transportation infrastructure. We don't do much in terms of vehicles and vehicle technologies. And I was trained as an automotive engineer before for my bachelor and master degree. When I came to the US for PhD for transportation engineering in about 22 years ago. At that time, these two fields, transportation engineering versus automotive engineering, they are very different fields. For cars, for automotive engineering, what we concern is individual cars in terms of the efficiency, the safety, as well as comfortability. What we study in transportation engineering is that we see cars as boxes following each other. Not much in terms of connection between the two. Nowadays, if you see these two fields actually getting a lot closer, to certain extent, these two fields actually get merged. Okay? What's happening in the future in terms of the transportation system? It's changing by adding a fourth component. The fourth component, I think, is a service component. Starting from the mobility services. In the future, people are still going to drive. Some of the people may still own their own cars. And that car could be an autonomous vehicle. But there will be a mobility service company provide transportation service and on demand. Okay? Also, if you look into the infrastructure, if you look at the vehicles, they're all changing. The infrastructure of the vehicles become connected and automated. If you look into the infrastructure itself is no longer just the pavement that the vehicles will run on. The infrastructure will be able to provide information services to help the connected and automated vehicles. As we will discuss, the single vehicle intelligence is not going to be sufficient for autonomous cars. That will be need for infrastructure support. So I think this is what I think in the future that will be intelligent transportation service, and there will be intelligent transportation service companies to help the government to run this smart infrastructure, to provide the support for connected automated transportation. Obviously, there will be communication services also, because vehicle and infrastructure need to be able to communicate. And we see this already. We see this already by the emergence of Uber or Didi. We see these already because we know Verizon, we know AT&T, they all provide communication services. What I think is emerging is the intelligent transportation services. To a certain extent, my experiment at Didi is trying to create this intelligent transportation services, and we're going to talk about that in my following slide. So, in the next, what I'm going to do, I'm going to look into these three major components from the perspective of services. And looking into each of these components, looking into the services, and tell you or let you know in terms of what I think are challenging issues. Okay, let's first look at mobility services. So I worked for the 2 years in Didi, and Didi certainly is a ride-hailing platform. It's a transportation platform. At the core of the business, there's a few things. One is they need to match the demand and supply. If you have a demand in terms of riding request, then they need to find where the supply is. And so you can think of a number of vehicles available, and these are obviously human-driven vehicles at the moment, and there's a number of requests in terms of travel. We need to match those. We need to consider, given the objective, to consider the platform efficiency. Also, we need to take into the consideration of customers' satisfaction. Once they are being assigned, these vehicles will be drive to the location, to the pickup location, and then pick up the drivers, transport the passenger, and then to the destination. Once they go into the destination, their position changed. Sometimes those are the locations has not enough demand. So we have to reposition these drivers or these vehicles. And these are the single traveler's request. On Didi's platform, also, in order to save cost, to reduce cost of travel, also to reduce traffic congestion, they also do provide carpool services. In fact, in Beijing, where the roads are very, very congested in the morning, from where I lived to my office at the time, about 6 kilometers. If I ride the bike, it's roughly about 35 minutes. If I take the car, if I drive, it's roughly around an hour. And oftentimes, because I don't have a car in Beijing, so I don't drive, so I take Didi, of course. The problem is that I can't even get a car. And oftentimes I wait 20 minutes. So what I do, I call carpool services. And usually carpool services has higher priority on Didi's platform, so you'll get it quicker in terms of the car. But you have to share the vehicles. And so when you share the vehicles, then the problem comes. Which vehicle and we carpool, which two or which three passengers? Obviously, we want these passengers to have either similar destination or along the way, along the trip. And the computation of that become much more complex. So on Didi's platform, most of these, in terms of dispatching, are computed or operated utilizing reinforcement learning. And by the way, the core of the algorithm also developed by one of the UM professors. And there was 2 UM professors in Didi, and Professor J-Ping Ye, he was the lead for the strategy development for the algorithm, for the dispatching algorithm. So if you look into some of these challenging issues on the core service in terms of mobility, one is demand supply forecast. We need to know where the demand is in the next 15, 20 or an hour, so that we can reposition these vehicles or drivers, or prepare for the demand, future demand. Route planning is very challenging in mobility services. We all know how to calculate the shortest path. Disastrous algorithm, A-star algorithm. But if you look at this from mobility service platform perspective, all of these are not sufficient. The reason is that on the platform every day we serve certain meeting trips. At the highest, in terms of the hour, there are more than million trips need to be served. Every day on Didi's platform, they make 20 billion routing requests. Because in order to match a passenger with a car, you have to search surrounding supplies. And after you search the surrounding supplies, you also need to estimate, in terms of estimate arrival time of arrival. And so not only you need to calculate the path, you also need to calculate the time. So there's a lot of routing requests being conducted. And the efficiency of the algorithm is the key to reduce the computational cost. Okay. The other thing I want to mention that pricing is also very important. Okay. Because there's 2 sides. On the platform, there's demand side and are also supply side. And the price is being determined by platform. If it's too high, then we scare away the passengers. If it's too low, then we don't have sufficient to pay for the driver. Okay? So pricing strategy is also very important. Also, traffic conditions, estimation of the traffic condition and prediction of traffic state for the future is also very much key to the business. Because when we calculate the estimated time of arrival, a lot of these really depend upon the traffic condition. Sometimes it's even the short distance, the travel time could be very long. And these are all key, these are all core items in transportation engineering. We study traffic flow, we do the traffic state estimation, do prediction. All of these are key to our curriculum.
So is the penetration rate of Didi vehicles high enough to impact traffic?
I'm going to talk about that. I think so. I think so. Particularly in some of the downtown areas. Also want to mention, this is also related with mobility service platform, is these new energy vehicles, electrical vehicles. And Didi is also the company has probably the largest number of electrical vehicles on the platform. At the moment, there are 40,000 electrical cars on Didi's platform. And then when you do the dispatch, you need to consider the status of the battery. And also when or where to charge these vehicles. So you can see, start from Didi's data, because there's a lot of vehicle trajectories. You know the path. And you can also suggest to the electricity companies to determine potential locations for charging stations. In fact, a lot of these on Didi's platform, there's also a unit which negotiate with either the gas companies or with electricity companies in terms of the price for charging or filling. So this is, although this is core business on Didi's mobility service platform, I was not much involved with their core business. Okay, but all these are issues presented in the current mobility service companies, and a lot of these issues related with what we're researching, what we're studying at the university. Okay, looking into second topic, autonomous vehicles. As a civil engineer, or as a transportation engineer, we usually think the development of autonomous vehicles is outside of our field. Okay? And this is either electrical or mechanical. Indeed, if you look into how autonomous vehicle works, it really depends upon the sensors, the perception systems. And beyond the perception system, there's also the planning of the trajectory, and then control of the vehicle. On top of that, you have to localize the vehicle by using the localization devices plus the high definition maps. So these are the key components of autonomous vehicle technology. Usually we think it's outside of our field. However, if you look into autonomous vehicles, the operation of autonomous vehicle, when autonomous vehicle drive on the road, then it's closely related to our field. Why? First of all, before we can deploy these vehicles on the road, we need to test and evaluate those. And previously, when we do the vehicle testing, and these are all really the responsibility of the OEM or the car company. Now it's no longer that. It's no longer that. Because we need to put these autonomous vehicles. Previously, driver has the responsibility. Now for autonomous vehicle, there's no driver. This is one piece of device will transport people. We need to make sure these devices or these tools are safe enough. So we need to do the testing and evaluation of the autonomous vehicle. And usually the testing of the autonomous vehicle has three categories or three types. A large portion of these are simulation. We do simulation in terms of autonomous vehicle testing. Then we do closed test track. We have a closed facility to test vehicles under specific scenarios. Then on-road test. Now, for all of these are closely related to transportation engineering, because we know in terms of either in the real on-road environment or in the closed testing facility or in the simulation in terms of the traffic, because we study traffic. So when we say test, what scenario we need to test? What are the background vehicles? What are the traffic patterns we should test? Not only we need to challenge these sensors, but also we need to challenge the intelligence of autonomous vehicles. So at University of Michigan, we have developed M-City. That's world's first closed test track facility. And if you look into any of the closed test track, there's no background traffic. It's closed empty test track. Autonomous vehicles can interact with the infrastructure, but there are no background traffic. And in addition to that, in terms of the emptiness of these closed test track, when you conduct testing and evaluation in the closed facility, sometimes you want to test these corner cases. When you test these corner cases, sometimes it's dangerous. For example, if you test the red light running across the intersection, if you use the real red light running and do the test with autonomous car, sometimes it's very dangerous. So that's why we developed this what we call augmented reality testing platform. So we use traffic simulation to provide the background for traffic pattern. We generate virtual vehicles and feed these virtual vehicles to autonomous system. So although there are no real vehicles within the facility, but to the autonomous system, they can see all of the virtual cars. They need to react and interact with the virtual car. In this way, you can actually generate any patterns you want. Congested pattern, uncongested pattern, emergency braking, and things like that. And you can test out these autonomous vehicles' capability. And you can use the real autonomous vehicle driving in a closed facility, but test out their intelligence of driving in various background traffic patterns. And so not only that, we also need to generate these scenarios. What type of scenario we want to do the test, and how we can test these autonomous vehicles' intelligence, just like a driver test. When you get your driver license, you all do the driver license test. There's someone sitting beside you and ask you to drive certain routes and see how you did your driving, do your driving task. The same thing for these autonomous vehicles. We need to test the intelligence of these vehicles for certain patterns. What type of pattern? What type of scenario? We need to test. If we rely upon the on-road test, and people have shown that if you rely upon on-road test, it takes years to test those, because 99% of the on-road testing are useless, because these are for example, if you're driving on an empty road, or you're driving in a situation of the car in front of you is very far, then no matter how long you drive, it doesn't matter. These testing efforts are wasted. So we need to generate these scenarios challenge enough to the autonomous vehicles. So what the scenario is. So how to generate this scenario. And all of these are closely related with transportation engineering. Okay? So we can look into the naturalistic driving data in terms of the driving behavior. We can look into the situations that might be more dangerous to human drivers. Now, if we combine these, we can generate these, we can create these scenarios which we can accelerate the testing and the evaluation of the autonomous vehicle. It turns out by using these methodologies, sometimes we can accelerate 10,000 times. Much faster in terms of testing and evaluation. Testing also is coupled with training. So if I can test you in terms of where you have problems, then we know how to train you also. So in this case, not only testing is important, by creating these testing scenarios, we can help to train these autonomous vehicles. Now we get into really the core business of autonomous vehicle development. I also mentioned that autonomous vehicles, their perception system have deficiency. They can only see those that far. For example, LiDAR, usually they can only see around 50 meters or as far as 100 meters. Beyond that, they can't really see. Now, if you look into the situations, and there are many scenarios that might be dangerous to autonomous vehicles. For example, if you have a pedestrian walk in front of a car, and your autonomous vehicle is at the back of that car. When this pedestrian walk out, because of the line of sight, this autonomous vehicle can't see. Sometimes create dangerous scenario. Same thing for vehicle merging or even with traffic light occlusion. There are scenarios, there's a lot of these type of scenarios. The perception system of the autonomous vehicles is just simply insufficient to detect these objects. Then what we do is that we want to utilize infrastructure to provide service to these autonomous vehicles to help them to actually know early in terms of these objects. Okay? So not only for the autonomous vehicle to drive to work, not only we will need the intelligent autonomous vehicles, we also need infrastructure support. And in the future, you will need cloud control also. So to do that, we will need to equip the new type of sensors on the road infrastructure. So the new type of sensors is not the detectors we're used to for either the machine vision detector or the loop detectors. These are the object detection systems. I will discuss also later on, I will predict that the detection system, the detector business in the future will disappear because vehicle itself, because of the connectivity, will become mobile sensor. However, these vehicles need support from the infrastructure, and the infrastructure support is coming from these object detection systems. It's not a flow detection system anymore. And obviously, with that, we will need to have connectivity. Either dedicated short-range communication, or 5G, or 6G even. So this is another work I did in Didi. I have a small team working with me to develop this cooperative vehicle infrastructure system. And this is the one we developed in the early, in January this year. This is the first testing intersection just right around the corner of Didi. And when I took a picture, one of my staff is actually standing on that platform. So you can see this is an unsignalized intersection, but it's quite congested, so we actually put a signal over there. And on top of the signal, there are 8 cameras, and at the side, there are 2 LiDAR and 1 roadside unit, communication unit. So you can see all these pictures. You can also detect all the objects. Later on at the intersection, in May, we'll also add millimeter wave radar to calculate the speed. And now the system has already finished in terms of the prototype development. And I was just being informed last week they start to install these in Suzhou, in one of the real intersections in Suzhou. Okay? So again, these seems like very different with transportation engineering, traditional transportation engineering. However, it's very much related with the real business. So the third component, as I mentioned, is road infrastructure management. And this is actually why I went to Didi for the leave absence. So I will talk a little bit in terms of the traffic lights control. So there's one of the, I would say, the most critical infrastructure, one piece of critical infrastructure for transportation management. In the US, there are more than 300,000 traffic lights. And most of the DOTs do not even collect any data from these intersections. And if you look into the transportation report card, this is 2012, there's 2017 also. Every 5 years also they conduct surveys in terms of traffic signals performance. If you look into traffic monitoring and collection, it has been F for the past 20 or 30 years. And there are a number of studies say if we re-optimize these signals, the benefit-cost ratio is 40 to 1. Very, very high. But we don't do it because retime each traffic light costs about $4,000. Just one time. So if you times by that by 300,000, it's very costly. So the key to the problem is we do not have continuous, reliable, also cheap data. And many of the traffic lights in the US, I estimate roughly about half, are fixed time. There's no sensors whatsoever. So even for those actuated or adaptive signals, and we utilize either machine vision-based sensors or inductance loop detectors, and oftentimes these detectors are prone to errors or malfunction failures. So if you look into connected vehicles, these connected vehicles itself are broadcasting their locations and speed. On Didi's platform, every vehicle, every service vehicle, communicate with the backend server every 3 seconds in terms of their location. So this is part of Beijing, and you can see in terms of the numbers of vehicles, the Didi vehicles. So if you ask me whether it impacts traffic, in some area it does. In some area it doesn't. So these vehicles itself can serve as mobile sensors. And the technology itself in transportation engineering is not new at all. In 1990s, we started to use what we call floating cars to measure traffic performance. However, we only have a very small number of floating cars, 1 or 2 or 3. And that's just too little, too few, and we can't really do much about it. But now if you see from mobility service, these are connected vehicles, and these have large numbers. Comparatively to the traffic itself, the penetration rate is still low, but it's sufficient large enough so that they can tell us in terms of real-time transportation performance. And with that, this can help us to manage the traffic light. And so, with that, now if you look into the intersection management, look into traffic lights, and we need to estimate in order to optimize, we need to estimate into either volume or queue or something like that, or delay. And the vehicle trajectory information actually are very rich. If we know a vehicle stop at the intersection between vehicle and the stop bar 100 feet, we know roughly around 4 vehicles. So that's queuing information, although I only know 1 vehicle. If I accumulate sufficient enough of data by every direction, actually I can estimate in terms of delay and also other performances. If I have enough performance measures, then I can optimize it, changing the parameter. This is just like if you have an engineer who observe that intersection multiple times, then you can actually utilize that information to optimize and retime your traffic lights. So if you look into how we did it in Didi's case, as I mentioned, the market penetration is still low. In most of the cases, it's below 3% in major cities in China. And because it's low, so some of the intersection doesn't have enough number of vehicles to cross to traverse. So what we do in this case is we develop the optimization platform into 2 parts. One is, we say, base plan optimization. We do it only 1 to 2 weeks. So in this case, we observe enough longer time, accumulate enough data so that we can optimize the traffic parameter, signal parameter, particularly these background parameters, the cycle length, the offsets, and things like that. Then dynamically, if we receive sufficient data, and if we see there are sufficient data to support us in terms of the delays with different directions, particularly at the congested situation, if it's either is oversaturated or spillover cases, then we can dynamically adjust the green speed, help to relieve these congestion. So in the future, if we have even larger number of connected vehicles, then we don't have to develop into two. We can, if we have enough data, we can just do it on the fly. But in the case, in our implementation case, we don't have sufficient data. And so what we do is we develop this two-stage approach. So then with that, as I mentioned before, most of the cases we do not collect data and monitoring these intersections. So most of the intersection is open loop. We leave it alone for sufficient enough time. Unless that intersection is too bad, then we retime. So it's an open loop operation. Now with that, we can do a closed loop operation. By the way, the best of this is that we do not need to invest on these on-road sensors, because all this sensor information coming from the mobility services. These are mobile sensors. We do not need to install these traffic flow detection sensors. This traditional open loop system versus now the closed loop system. The input are different. The input are measured from the flow. Now we utilize trajectories. And this is an open loop system because once we develop the plan, we leave it there. We don't have time, we don't have budget to retime it. And now with this, because the data coming from the outside, now we can actually optimize every week, dynamically every few minutes. In Didi's case, every 2 minutes. So if you look into this, we can offer this as a service. So this is within this dash line, these are all within the agency. Agencies operate these traffic lights. But we do not need data from agency. All of the traffic data is actually coming from the platform. We process these data. These are on Didi cloud services. And we push the optimized parameters into the traffic control system. And there are, as you can see, there are multiple switches. So because the system, the information is coming from outside, they can anytime they can switch it off. For example, if you have a preemption services, then you can switch it off and you can control the system on your own. So if you look into the transportation traffic signal control, the development of this technology. At the very early, 100 years ago, we do single intersection optimization. Once we add communication, we can do coordination. Once we add detection, we can do vehicle actuation or adaptive. And in the future, when vehicle become automated, then we don't need physical signal. So the way, the one we developed, by the way, the technology actually developed at the U of M, and Didi acquired a license from U of M to deploy. And the technology we deployed is somewhere around here. It's not a fully adaptive signal system because sometimes we cannot respond in real time because we do not have data. But it's dynamic. Every 1 or 2 weeks, we do optimization. And sometimes when we have enough data, we also dynamically update the traffic parameter, traffic light parameter. When we have more data, then obviously they will move into more real-time adaptive, or even in the future for signal-free operations. So this has been implemented in a number of cities in China, and this is the main work I did in Didi for the past 2 years. And this is in the city of Liuzhou with 250 intersections. This is on the fly. This is right now. It's even at the moment it should be operated by Didi Co. And this is one of the examples to show you before and after. And these are cities downtown. This is a new CBD area. And if you look at the video a little bit, you can see a lot of the red color dots. And every dots here are Didi cars. And you can see a lot of these red dots, the slow vehicles accumulated. And if you can see from the right-hand side, it's much lesser in terms of the red dot. And the speed is significantly improved. So before I left, this has been implemented in about 20 cities. On the platform, there are about 1,300 intersections. That's still a very small number. China has, my estimate, has 200,000 intersections, signalized intersections, a little less than the US. But this is the starting point. And we offer this as a service to the cities. So this is not a product. This is a service. So being charged by service fee. And if you look into the platform economy, sometimes the real platform doesn't earn money. The platform is to get the user. Once you get a user, there are other approaches to earn money. And this is our approach. The other approach, we offer this very cheap services for traffic signals. But once you get into the door, you will see these DOTs has a lot of other things you can do with them, and they need your help. One thing they really need help is data management. DOTs collect over the years a large amount of data, and all of these data are segmented. They are not connected. They are not being utilized. And even different branches, they have their own data. None of these data are really shared. So data center for DOTs is very, very important. So one of the things we do in this business unit is to work with DOTs to help them to manage the data. Although we call it smart transportation, green or whatever, this is essentially a data management center. And particularly with this data center, not only we help them to manage the data, to clean the data, we also need to figure out the relationship among the objects within the data. We need to create what we call knowledge graph within the data center. So once you create these relationships, you create these relations, now you can utilize these data for multiple purposes. Okay? And our first implementation of these is actually in the city of Jinan. And in city of Jinan, all the DOT's data collected and stored on Didi's platform. But this is a private cloud. This is not on the Didi's public cloud. It has a large number of data sources that include not only the detector data, the video data, the bus data, the special vehicle data. There's a lot of data is actually collected on these. And the core business of these is to create the knowledge graph within different objects of the transportation system. So, I want to summarize what I think in the future. the three components, major components, are connected by services. Trawlers will become multimodal, ride sharing, one-stop services, and these are the trends in terms of from trawler's perspective. Cars obviously become more connected and automated. And the infrastructure side will be from independent become more cooperative. And among all the big data and artificial intelligence are all very important, but I also put transportation engineering at the core of it. Indeed, if you talk to any of the DOTs, nowadays even you talk to the OEM, the automakers, they actually will recognize in order for this connected automated system to work, they need transportation engineers. Okay, so my last slide is to acknowledge my research group over the years, and this is the latest picture I can find. I'm still quite old, and has some of my current students are not in the picture, but that's the latest picture I can find. With that, thank you very much. Questions? Sure, go ahead.
Thank you, Professor. Actually, I have a question about your work with those DOTs, because based on my experience with those DOTs, they actually for a provincial DOT, they have many divisions, and for each division, they have their own data centers for their own data management strategies. So in your work, you said that you are helping DOTs to manage their data and come with solutions to improve the transportation system performance. So basically, since they have lots of those divisions, do you use a single solution, or for different divisions you come with different solutions?
That's a very good question. What I should say is that this surface transportation system is being managed mostly at the city level, not at the provincial level, not at the district level, at city level. In order to do that, in order to do this big data centers, create knowledge graph, the first thing they will do, actually not us. We can help them in terms of technology, but we cannot help them to break the barriers of different branches. So the first thing they will need to do is organizational changes. So if you look into City of Jinan, before they embark on our services, they actually create a new office. This office oversees all data within the DOT. So they coordinate all the branches, and we provide service for this office. And they call Smart Transportation Office, and Smart Transportation Management Office within their DOT. So organizational changes is very important. But that's the trend. You can see other cities is following.
I have a question on the usage of the trajectory data. So, what is the market penetration rate for the vehicle trajectory data to have a very accurate prediction of traffic conditions?
We tried. This is a very good question. This question is part of his dissertation. It's going through 2-3 dissertations now. The first dissertation was not able to answer that question. The second dissertation was not able to answer that question, and we give it to the third. We don't know. But there are heuristic approach we can take. So for example, when we do these dynamic optimization, we mainly to detect congested pattern. The congested pattern have only two we care. One is oversaturation, one is spillover. Okay? And both of these two are severe congestion. And both of these two has very, I would say, pronounced features from vehicle trajectory. Because for oversaturated intersection, vehicles take two stops. If you get one vehicle have two stops, and you realize this is a reasonable vehicle, then you know it's oversaturated. Spillover is the same. Okay, and because this upstream intersections cannot move vehicle and the upstream intersection. And so if the vehicle stop at the upstream intersection, and you know it's green light, and this is spillover. So how many of these can confirm? We use 3. Why we use 3? Because we don't have theory to guide us. We use 3 to make sure we know it's really happening. There are studies from simulation, from half simulation, half real, and sometimes they say 15%, sometimes they say 20%, somebody say 50%. I don't even know, but that's a question need to be answered. We oftentimes being questioned.
I have a question.
Yeah.
You don't have to answer. Okay? Stay on the spot. So in the last 2 years, you transitioned from a professor to be a VP and chief scientist in the industry, right? So what was your biggest lesson learned? You can share with the audience.
It's a very good question. I will try to answer it. As a professor, as a researcher, what we do is to spend money. We convert money into knowledge. And that's how we do research. We ask for funding, we convert that funding, we educate students, and then we create knowledge. In a business, we convert that knowledge into money. So it's really different. The mindset is very different. As a professor researcher, I'm not so concerned about the budget. I ask for enough money to support a team for a project. In a business, now to run that business, the cost associated, the profit associated with it become very important. So the biggest, I would say, lessons I learned is that business, if you run a business, you need to run a business. So when I started to run a business, I start with a professor mindset. So that doesn't work. Eventually, there will be limitation, there will be constraint, and there's only that much you can do. You have to do better within the available budget. And so the mindset is very, very different. I should say, I oftentimes joke with my students. Before I went to the industry, I was trying to encourage every one of my students to become a professor. Every one of my PhD students. I graduated only 8. Half of them are professors, half of them are engineers. After these 2 years, either way, it's fine with me. The reason
You was 50% professor, 50% engineer. Either way was fine with you anyway.
my 8 students graduated. before I left, was 4 of these are in the industry, 4 of these in academia.
So you weren't happy with those 4?
Sort of. I was trying to encourage them to be in academia because I really like to be a professor. I thought, professor is a really good job. And after these 2 years, my thinking has changed. Mostly because I find industry has very challenging problems.